In this unit, we're going to talk about intermolecular forces and liquids and solids. So let's start with the idea of intermolecular forces, or that forces that attract and repel molecules together, or apart. So we have intramolecular forces, which are our covalent bonds and ionic bonds, which create molecules, right, from atoms. So you have charges related, your charges involved with ionic bonds, and then you have partial charges and a difference in sharing of electrons with covalent bonds. Those are called intramolecular forces. The difference here is that intermolecular forces are the forces and bonds between molecules. So these are electrostatic forces, so positives and negatives charges still are involved here, but on average, these intermolecular forces are a lot weaker than the intramolecular covalent and ionic bonds. So types of intermolecular forces we'll talk about, but examples would be hydrogen bonds that hold water molecules together in liquid or in ice, solid ice. Or we have different types of dispersion forces, dipole forces that hold polar molecules together, and so forth. But it all relates to kinetic energy and the energy involved with the movement of the particles. As we increase the kinetic energy, we increase the temperature because by definition, the temperature is the average kinetic energy of a set of particles. So as we increase that kinetic energy and temperature, the particles get more degrees of freedom. So we have a solid, which has the lowest degree of freedom. There's some vibrations in there, but nothing crazy. Then we have liquid, which can flow, but it has a fixed volume. And then gas can kind of break the rules and take the volume of the container, take the shape of the container, and there's not many intermolecular forces between gas particles. But we'll talk all about that. So in general, the attractive forces follow Coulomb's law, where you could see delta H, which is enthalpy or the heat of heat or energy of a chemical process, where enthalpy equals C, which is Coulomb's constant, the charge of an electron, times the positive charge times the negative charge. So if you have, let's talk about an ionic relationship, which we're all familiar with. Let's say calcium chloride, right? Where CaCl2. In calcium chloride, calcium is 2 plus. That means Z is going to be 2. And then the other Z is going to be minus 1 or just 1. So that means the total charge is multiplied together is going to be 2 times 1, which is 2. If you had another type of ionic bond, like let's say aluminum phosphate, all right, aluminum phosphate is a very strong interaction because aluminum is 3 plus and phosphate is 3 minus. So you're doing 3 times 3, which is 9. So the enthalpy, or the lattice enthalpy, or the energy required to break the interaction of those those atoms, in aluminum phosphate's case, would be 9 times greater than, let's say, sodium chloride, which is 1 and 1. So the point there being that the charges or the partial charges have a great influence, and the greatest influence, on how strong the intermolecular forces are. The second influence is the distance, r0, right? R radius. So if you're seeing the energy is directly proportional to the charge. If you increase the charge, that means you're increasing the strength of the interaction, right? Which means the energy required to break it is higher. Divided by radius. So if the radius gets smaller, that means this number gets bigger, which means enthalpy gets bigger. So the closer and stronger the interaction, the more energy required to break it. This is kind of common sense, but here it is in equation form. So we'll talk about these intermolecular forces. We have dispersion forces, dipole-dipole attractive forces, and then we have hydrogen bonding, and then we also have ion-dipole, which for some reason is not here, but we collectively refer to all these terms as van der Waals forces. These are intermolecular, right? So they're in between different molecules. So if you look at these two polar hydrochloric acid molecules, they create a dipole-dipole interaction because we have partial positive charge on the hydrogen and partial negative charge in the chlorine. So you have that positive and negative will make an interaction intermolecularly, meaning in between molecules holding them together, which is a lot weaker than our intramolecular, which is between the hydrogen and the chlorine, our covalent bond. So first, dipoles are anything that is polar, but even non-polar molecules can exhibit a dipole. And we refer to this as a dispersion force. So a dispersion force is when you have non-polar molecule. Well, really any molecule can have a dispersion force, but generally the dispersion force is the main intermolecular force in only non-polar molecules. And that's because dispersion forces are the weakest intermolecular force. Because they're so weak, in polar molecules, you have dipole-dipole interactions, sometimes hydrogen bonds. Those interactions are tenfold higher in strength than the London dispersion forces, making these kind of negligible, except for when you have nonpolar molecules. Nonpolar molecules, this will be the only force that they exhibit. So what happens is how can two nonpolar molecules that do not have a difference in electrons in from one side of the molecule to the other, how can they create a dipole, meaning a molecule or a particle that does have a charge difference? And the answer is they can collide, right? So they can collide, or they can have some type of collision with an outside atom, or just collision with a container. They can collide with something, and their constant motion and collisions can rattle around the electrons in the molecule, and they can be rattled around temporarily, making there an unevenness in the electrons on each side. So the way I explain it is, if you have two molecules that are, let's say they're snow globes. Snow globes, you have all the snow particles. If you shake a snow globe, or if you give it motion or hit it against another snow globe, assuming they don't break, the snow will go everywhere. The snow will move to one side, move up, move down. The snow particles are the electrons in this case. So as you make a collision or you cause any type of disturbance, these electrons, they're just located in a snow globe, or kind of spherical molecule, they will move to one side. And this temporarily charges the particle, right? If all the electrons move to the back side of the molecule, that means the back side is going to be negative, the front side is going to be positive, like we have on this right molecule here. And what that'll do is, because you have that temporary, or what we call an induced dipole, it is induced by motion, by collisions, and neighboring atoms. It will also induce the neighboring molecule. So if the neighboring molecule, which has electrons that are distributed throughout evenly, sees another molecule that was just affected by this dispersion force and has a positive and a negative end, all the electrons in that neighboring molecule will rush towards that positive pole, making a temporary dipole on that secondary molecule, which can then, as you can imagine, cause a chain reaction of temporary dipoles within the entire mixture. So this is what we call an induced dipole. Think about two snow globes hitting each other. Temporary movement of the electrons, which creates a temporary charge differential, temporary dipole, and then eventually over time, what happens to a snow globe? All the snow settles. And then you go back to your nonpolar waves. So this is called a dispersion force. The trend in dispersion forces, you have the radius. As you get larger in radius and in molar mass, the dispersion forces increase because you have more surface area and more electrons to move. So big snow globe versus small snow globe. A big one that has more pieces of snowflakes, you're going to have a greater polarizability. That's the word we use here. So it's a greater polarizability. As you get larger, you have that. And then the one way we can represent or at least compare molecules using the intermolecular forces and dispersion forces, is by boiling point. So if the boiling point is higher, that means it requires more energy to break apart those intermolecular forces. Same thing for melting point. It requires more energy to break apart the solid bonds to make them into more liquid. So keep that in mind as we go on. The boiling point is going to be the trend. So the idea is, for mass, larger molar mass means you have more electrons. Larger electron cloud, increased polarizability, stronger attractions. The shape of the molecule also matters. The shape also matters, because if you have an open fist versus a closed fist, which one has more surface area? Which one will displace more particles if you hit something? You'll make more of a noise if you use an open hand, right? That's why we clap. The reason why that is because our hand creates a larger surface area to displace more particles quickly to create a sound, right? If we use a closed fist and clap together, we're making not much sound because the surface area is small and also it'll hurt like hell. So the idea is that a large surface area of contact means you have more electrons, more places of interaction, more molecule displacement, or more electron displacement, I should say. So here's three molecules that all have the same arranged, same formula: neopentane, isopentane, and N-pentane, which is, these are all 5-carbon hydrocarbons. And you see, as you increase the surface area, the boiling point also increases, but only by a little. And as you saw from before, if you increase the size, you can say you keep doubling the molar mass, the boiling point goes up by a more dramatic amount than just a few degrees. Here we're going up by 10 to 20 degrees. Here we're going up by hundreds, maybe 100 or 200. Anyway, so if you have CF4 and CCl4, CCl4 is larger, so that means it's going to have more dispersion forces, and it's going to have a higher boiling point. So that's why CCl4 is liquid at room temperature, because it has a higher boiling point, because it has more intermolecular forces than CF4. All right, so next we're going to talk about dipole-dipole attractions. Now, the dipole-dipole attractions are between polar molecules, and they're stronger than dispersion forces. So all polar molecules have a uneven distribution of electrons, and this gives them polarity, right? This gives them negative charge on one side, positive charge on the other, and the dipole has a net, there's a net dipole. So when you have net dipoles, they are going to arrange it to next to other molecules that are dipoles in a negative to positive fashion. So if we look at these, which one will have a dipole-dipole interaction? You're looking for the one that is more polar. So A is nonpolar, B is perfectly nonpolar, C is also nonpolar, and then so D is your answer, because it's fluorine. Is the most electronegative. All the electrons will go towards the fluorine, making an uneven distribution. All right, next, hydrogen bonds. Hydrogen bonds are dipole-dipole interactions on steroids. They are the strongest ones. So the reason why is because there's the largest difference in electronegativity in molecules that can have hydrogen bonds. And the reason why is because there are 3 key elements. So it's whenever hydrogen is bound to either one of these: nitrogen, oxygen, or fluorine. When you have hydrogen bound to one of these 3 elements, it can make a hydrogen bond with another molecule nearby with hydrogen or one of these 3 elements. So, and that's because of electronegativity. You have so it's an unusually strong dipole, and it's, remember, the most important thing is those 3 elements: nitrogen, oxygen, or fluorine. So here's the example on the bottom here showing the hydrogen bonds with water. So they are simply the same as dipole-dipole, right? Because you have a positive pole with hydrogen, negative pole with oxygen. So they will arrange themselves negative to positive as such. And here's where hydrogen bond plays a role in boiling point. As you can see, once we have H2O or HF or ammonia, these 3 molecules can partake in hydrogen bonds. Their boiling point shoots up compared to other elements in their class or in their group. Oxygen, sulfur, selenium, tellurium, these are all in group 6, right? A group of 6A or 16. Sulfur is not polar enough to go through hydrogen bond or have hydrogen bonds. Neither is selenium, neither is tellurium, but sulfur, selenium, tellurium increases in size tremendously going from those 3. That's why the boiling point will increase. But looking at the smallest of that group 6 is oxygen, but it happens to have the highest boiling point, and that's not by chance. That's because it is an anomaly and has a very high electronegativity, so high that it is a large difference away from hydrogen, and it can form really, really strong dipoles. The same is true for HF and then NH3. So intermolecular forces are important in everything, including DNA. So our DNA base pairing is made by hydrogen bonding. So it's extremely important. We can talk about this another time, but it's very important. The last one we'll talk about is ion-dipole. So an ion-dipole is basically, think about this: salt dissolving. The way salt is going to dissolve is you take a crystal of salt and you put it into water and you mix it. what is happening on the molecular level when you are mixing something is that the water molecules are individually attacking the crystal. The negatives of the water, meaning the oxygens, will stick to the positive, in this case it's potassium, the positive potassium. The positive ends of the hydrogens of the water will attack the chlorine, and it will eventually be ripped apart. The crystal will come ripped apart by the water molecules. So this is the ion dipole. And it's also fairly strong. It's on the same order as dipole-dipole, and it could even be a little stronger than some of the dipole-dipoles because the ions have generally a more polarized charge than covalents do. So here's a list of bond strengths. You have a single bond. You see, I mentioned in the beginning that these intermolecular forces are at times tenfold or more weaker than intramolecular. So if you look at a single covalent bond of carbon-carbon, the bond strength is 346 kilojoules per mole. That's massive. That's more than tenfold higher than most of these intermolecular forces, hydrogen bonding being the strongest, ion dipole being up there as well, dipole-dipole in the middle, and then London dispersion is very weak. Next, we'll talk about liquids. So viscosity. Viscosity has a direct relationship to intermolecular forces. And you can imagine, the more intermolecular forces you have, the higher the viscosity, because you have greater bonds holding the liquids together. And the same is true with surface tension. Surface tension decreases as the intermolecular forces decrease. So there's a lot of knowing your intermolecular forces gives you a lot of power because you can not only know about boiling point and compare molecules with boiling point, you can know about viscosity, you can know about surface tension, and you can also know about vapor pressure, which we'll talk about.